Okay, here we see a boat that's heading upriver at 2.2 meters per second relative to the water. So that is the motion of the boat relative to, oh my goodness, the motion of the boat relative to the water. Um, Here we see the motion 0.4 meters per second upriver. Well, that's an indicator of the motion of the boat relative to the shore. Since I'm really talking about boat, water, and shore, the relative velocity equation tells me the motion of the boat relative to the shore is equal to the motion of the boat relative to the water plus the motion of the water relative to the shore. Now, anytime we're doing this, we do need to keep in mind we're talking about vector addition. So vectors in opposite directions, they're going to cancel each other out. In this case, let's just imagine that the flow of the water is this direction. Well, I'm going to have to add the motion of the boat relative to the water plus the water relative to the shore. And I know that the end result, if I add these two vectors together, is that the end result, all right, this is boat relative to the water, add that to water relative to the shore, and the end result is this motion of the boat relative to the shore. I've got things in different directions. If I choose right to be the positive direction and left to be the negative direction, then this would, in this horizontal direction, turn out to be negative 0.4 meters per second is equal to negative 2.2 meters per second plus whatever that motion of the water relative to the shore is. So I add 2.2 to both sides, and I would get the speed of the water relative to the shore. It's going to be 1.8 meters per second, and that will be moving against the boat. If it was moving with the boat, we would have observed that the motion of the boat relative to the shore was greater than the motion of the boat relative to the water because I'd be adding them together in the same direction. In this one, we have an airplane that is flying due north. All right, that's the heading that the airplane takes, and it has an airspeed of 140 kilometers per hour. So I can say this is the motion of the plane relative to the air. Anytime we're talking about wind, wind is always going to be describing the motion of the air relative to the ground. So as you can imagine, if this plane flies north while the wind is blowing, I'm going to end up watching this plane head off somewhere in this northeast direction. Well, when these are perpendicular, that's pretty simple because I know Pythagorean theorem tells me a squared plus b squared is equal to c squared. So in this case, I have 140 kilometers per hour. I have 75 kilometers per hour. And so if c is equal to the square root of a squared plus b squared, I'm just going to say the speed of the plane relative to the ground is equal to the square root of 140 squared plus 75 squared. And that results in a ground speed that would be, for me, 158.8 kilometers per hour. If I did want to know what this direction was, first off, I would know that the way that this is drawn, that direction would be described as east of north, and I could do an inverse trig function. I could say tan to the negative 1 of the opposite of that angle would be 75. The adjacent would be 140. Make sure that you are in degree mode. And that would be 28 degrees. But I have to say, in relation to what? Well, it's making an angle, right? And my vertical axis is north, so I'd say east of north. All right. Number 3, I'm going to make a separate video for that one because it seems that people have a lot of questions about that one. So let's looking at projectile motion in general, free fall motion in general. An object is shot straight up and it rises for 6.5 meters per second before it reaches its highest point. A different object takes 6.5 seconds to reach the ground, and it's falling from rest. If I'm going to compare those two displacements, well, one thing that we need to keep in mind is that when we talk about something going up and down to the same height, we do get to say that the time up is equal to the time down. We also know that in the vertical, when we're looking at a projectile, we have rest at the highest point. And so that means that you would observe to have the same distance. If you're on your way up for 6.5 seconds, and then you're stopped, and then you're on your way down for 6.5 seconds, that means that it's the exact same situation. For this type of situation, another thing that we can remind ourselves of is time up. Right? We're always remembering that our vertical velocity is 0 at the highest point. So if I think about trying to solve for the time that we go up, I could say 0, right? Final velocity is equal to initial velocity plus acceleration times time. But in this case, if I say that my initial velocity is directed upwards, I could probably say that my gravity, acceleration due to gravity, is directed downwards. And so just by subtracting and dividing, well, the signs will cancel out. I'll get a positive time. That's good. Time up is just equal to the initial velocity. If you're doing projectile motion, you might want to specify that it is a vertical velocity. Acceleration due to gravity is vertical over t, or sorry, over g. If we're looking at our time down, one thing that we can use for our time down is to say, well, if you're falling from some h. And if we chose down to be the positive direction, I could say, well, the height is just equal to, well, there is no initial velocity, and so I can say 1/2 gt squared, and I see that time down is equal to 2h divided by g, take a square root. This is a unique solution too, if you think about it. Knowing that these two things are equal to each other, you actually would have the ability to set this equal to this, and you could solve for the height. But it is important that we realize that the time up and the time down are the same. That means if it takes the same amount of time to go up as it takes to go down, you're talking about the same displacement. Can the velocity of an object change when its acceleration is constant? The whole definition of acceleration is a rate of change in velocity. All right, we do have VF is equal to VI plus AT. That's our standard equation. Acceleration is VF minus VI divided by T. That is specifically change in velocity over time. So yes, anytime you have acceleration, you will have changing velocity. Can a car have a negative velocity and a positive acceleration at the same time? Let's just remember that when we're thinking about signs, signs don't tell us about increasing or decreasing. Signs give us direction. All right? That's all the signs of all these vector quantities are telling us. Okay? So, that means that something is moving in a particular direction. Let's say we have our velocity. And the velocity is negative and the acceleration is positive. Well, what we really need to understand about this description is to say, well, the velocity and acceleration are in opposite directions. That's all that means. In this case, if my velocity, right, is decreasing, or if my speed is decreasing, that means that my acceleration is in the opposite direction. Anytime acceleration is in the opposite direction of velocity, you're describing a situation of slowing down, all right, decreasing speed, because speed doesn't have a direction. And if I flipped these and I said positive velocity and negative acceleration, that would be describing the same thing. Can the car's velocity change while it is traveling with constant acceleration? Absolutely. Again, acceleration describes the rate of change. So that just means if the acceleration is constant, you have a smooth kind of change in velocity. It's not like when somebody kind of rides the brakes for a little bit and then realizes they misjudge it and then they got to slam at the brakes. That would be changing acceleration. But any time where you have acceleration, the car's velocity changes. The specific one says velocity changes signs. That's true too. It would be kind of hard to, well, if the car was going up a hill, stalls out, and comes back down, let's just think about this graphically. Acceleration is the rate of change in velocity. So can I have a graph with a constant slope that crosses the axis? Absolutely. So in this example, you'd see the car slows down and then stops and then comes back down. This maybe could be a car, like I said, that stalls out while it's rolling up a hill and it stops for a minute and starts rolling back down the hill. So for projectile, any kind of projectile free fall motion, free fall is just going to correspond to when our acceleration is equal to gravity, where that acceleration is approximately 9.8 meters per second squared downward. So I have a ball. It falls a distance of 4 meters. And we're assuming that my initial speed, anytime you see drop, you're assuming that your initial speed is going to be 0 meters per second. Looking at our kinematic equations, df is equal to di plus vit plus 1/2 at squared. Since everything is moving downward, I'm just going to choose downward to be my positive direction. If I had a coordinate system where I said that my final position was 4 and my initial position was 0, right? Let's just choose my object to be the center of my origin and downward to be the positive direction. I'd say 4 is equal to 0 plus 0t plus 1/2 g t squared. And we get that same kind of relationship that we did in the previous one, solving for the time down. 4 is equal to 1/2 times 9.8 times t squared. I end up with 4 divided by 4.9 is equal to t squared. Take a square root. And I would get time, for me, equal to about 0.9 seconds. When something is thrown up, it's typically a good idea to stick with upward as your vertical coordinate. It's launched upwards at 25 meters per second. I know that it's going to go up, stop, come back down. I know that my acceleration is downward at 9.8 meters per second squared. How high does the ball rise? There are two different ways that I could solve this. The first would be to say, well, I know it goes up to some maximum height, and if I get my signs right, I could say h is equal to 25t plus 1/2 times negative 9.8 times t squared, but I don't have the time up yet. So I'd have to go ahead and use my velocity equation and say 0 is equal to 25t minus, or say plus, negative 9.8. Oh, my mistake. 0 is equal to 25 plus negative 9.8 t. Now I can solve for the time up like we did before. What was that? It was vi over a. Well, that's what we're going to end up with, negative 25 over negative 9.8. And that would be 2.55 seconds. Once I have 2.55 seconds as my time, then I can go back to h, plug that in, and h is going to be equal to 25 times 2.55 plus 1/2 times negative 9.8 times 2.55 squared, giving me a maximum height of 31.88 meters. Now I got that again by subbing that time in here. If all we're concerned about is how high the ball rises, and we don't really care about how long it's in the air, how long it takes, I could also use the VF squared equation, 2a delta d, where I can say that my final velocity is 0, initial velocity is 25, acceleration is negative 9.8, and the change in position is really just that height, the maximum height that it's going to reach. Either one of these is going to give you the same result. You can try it both ways. should get about the same result. How long does it remain in the air? Well, I figured out how long it took to go up. So how long it's in the air is really what we might think of as our total time. That's just going to be 2 times the time up, which is going to be about 5.1 seconds based off of that calculation. So we go back and we think about Newton's laws. Newton's second law is the one we use most often. If you push a book, all right, let's just assume that that even if that is the net force, if that's the only force acting on this book, the net force is equal to mass times acceleration. So our net force and our acceleration are always in the same direction. But as we already looked before, we can have a velocity directed one way with a acceleration or net force directed the other way. That just means you're talking about slowing something down. Acceleration and velocity in opposite directions is possible. It's just always going to correspond to decrease in speed. Again, we're thinking about the proportionality of our net force equals mass times acceleration, or we rearrange that and we look at acceleration is equal to the net force divided by mass. You can see that our acceleration is directly proportional to the net force, inversely proportional to the mass. So, if I have the same force, okay, but I end up with a larger acceleration, that must mean that I have that same force act on a smaller mass. Specifically, if the acceleration is 3 times as large, that must have been because my mass was 1/3 the amount. Whenever we talk about weight, we're talking about the force of gravity. A lot of times, objects are described by their mass, at which point we would need to calculate their weight, okay, as the product of mass and gravity. In this case, right, mass is in kilograms, weight is in newtons, so that is my weight. I would have to solve for my mass. So in this case, I'd say 556 newtons is equal to mass times 9.8 meters per second squared. Of course, I'm going to have to divide by 9.8 on both sides. If you're trying to follow along, that would be a mass of about 56.7 kilograms. If I was on the moon, well, that's a different g, right? So we could say, you know, this g just depends on where we are. If I was talking about my weight on the moon, we'd say Fg for the moon is going to be equal to 56.7 kilograms times the 1.6 meters per second squared. And that would be only about 90 newtons. All right, the old elevator problem. Standard in really making sure that we understand how to set up net force, mass, and acceleration. So this person is standing on a scale, and so really there's only 2 forces that are acting on this person, the upward force of the scale and the downward force of gravity. without even knowing anything about my acceleration, I can look at this free body diagram and know that the net force, right, we say the sum of our forces is equal to mass times acceleration, but specifically I have to look at a free body diagram to determine what that sum is. So I can say here, the way that these forces combine in opposite directions, the upward force of the scale, the magnitude of that force, minus the magnitude of the force of gravity is going to be equal to, all right, mass times acceleration. Now, the way that I set this up is with upwards to be my positive direction and downwards to be my negative direction. Whichever way I do it for net forces, up minus down, right minus left, it's whatever positive direction I have minus whatever negative direction I have. Since I know my mass is 80 kilograms, I know that my force of gravity is equal to mg. So I take 80 times 9.8. And no matter what this elevator does, my force of gravity is going to be 784 newtons. That part is not going to change. Depending on the motion of the elevator, though, I would have different results. If we're at constant speed, and I know that that means my acceleration is equal to 0, then I know that these two things have to be equal, and I would just say 784. What happens when the scale is slowing as it moves upwards? Well, slowing down corresponds to acceleration being in the opposite direction of velocity. So in this case, I know that my acceleration is downwards at 1.6 meters per second squared. So that equation I have up here is going to say the force of the scale minus 784 newtons is equal to 80 kilograms times a downward acceleration. So I'll say negative 1.6 meters per second squared. Okay? So when I multiply 80 times negative 1.6, I'm going to get negative 128. But I'm also going to add 784 to both sides. And that gives me an end result of 656 newtons. That should make sense because if my acceleration is downward, I would expect to have a net force downward, which means my downward forces are stronger. Sorry about that interruption. Now we're looking at what force the scale would exert if it speeds up while moving downward. Well, if it speeds up, gets faster and faster and faster, that means our acceleration is in the same direction as our velocity. In this case, downward. So that means that our acceleration is the same as in section B, and we would expect the same result. Whether you're at a constant speed upward or a constant speed downward, constant speed corresponds to an acceleration of 0, which would be the same as part A. So hopefully one thing we can learn from this one is that the direction of our motion is not nearly as connected to net force and those things as the direction of our acceleration. If the elevator slows to a stop, the magnitude of the acceleration, the magnitude and direction of the net force really depend on the direction that you're moving as you go to a stop. So we know that if you're stopping while you move upward, your acceleration is downward. If you stopped while moving downward, your acceleration would be upwards. If a car is driven due west, 135 kilometers, and 80 kilometers due south, again, our resulting displacement, and I'm adding these two together, head to tail, one displacement plus another displacement will give us our total displacement, that straight line that connects beginning to end, and I can find that simply through the Pythagorean theorem again. Now this is my right angle. This would be the hypotenuse, so I got to remember 80 squared plus 135 squared is equal to that distance, or my displacement, squared. So I would need to take a square root to solve for the actual displacement. And that should be, with these numbers, 156.9 kilometers. When we look at objects that are on level surfaces, okay, there are certain forces that we will just automatically know the direction of. Force of gravity always acts downward. Normal force always acts upward. The frictional force will be parallel to the surface, so in this case either to the right or to the left, and here we have a force to get something to start moving. So we know that we're applying some force. Let's just say the force is to the right, and let's say there's some frictional force which is going to be to the left, force of friction. Some people tend to get confused with normal force and net force. A singular N is always indicative of the normal force. You also never put a net force on a free body diagram. That's something that you would really deal with later. We just want to see how these forces interact with each other. Now, anytime we're dealing with something in two dimensions, I want to make sure that I think about things vertically and horizontally, one dimension, then another. Oh, I don't know why that happened. So in the vertical, we're going to try and start. We're dealing with forces. So we say net force is equal to mass times acceleration. In the vertical, I have the normal force minus the force of gravity is equal to mass times acceleration. In the horizontal, I say that that force applied minus my force of friction is equal to mass times acceleration. Now, if you think about applying a force to a couch, you know that you're not going to move it with any force. There's a minimum amount of force. When we look at the force of friction, we also see that the force of friction doesn't really have a minimum value, but for static friction, it does have a maximum value where the coefficient times the normal force would give you the maximum value for that frictional force. So even though moving the couch horizontally might involve just these two, our friction force is related to the amount of normal force that we have, so that is something we need to pay attention to. With a little bit of substitution, and actually let's just think about this, right before it starts to move, we're really talking about an acceleration equal to 0. So if I try to calculate the normal force, I say normal force minus, well, force of gravity, we always have that equation for our force of gravity, mass times acceleration due to degree. So I have normal force minus mg is equal to, well, he said our acceleration is 0. Oh, that means in this case, because there is no vertical acceleration, and really anytime we're on a surface, there's not going to be any acceleration in the perpendicular direction. Normal force is equal to mg. Normal force is equal to 1,283.8 newtons. When I make a substitution for the frictional force over here, I can say mu times Fn is equal to m times 0. Oh, well then that force needed to get it to start to move is going to be equal to mu Fn. And I can see with a little bit of substitution, 105 is equal to mu times 1,283 newtons. So by dividing that, 105 by 1,283, I would get 0.08 as my coefficient of friction. Since the coefficient of friction is a ratio, let's just go back and rearrange this equation here. I'd say mu really expresses the ratio of my force of friction to my normal force. Well, since the units of both of those are the same, when I divide them, I actually just get no unit. So there is no unit for our coefficient of friction. It is a unitless value because it's really just expressing the ratio of those two things.